Okay, today we will continue our discussions on the generalized rotating field theory, which is considered as a very powerful tool for steady state analysis of induction motors with any type of asymmetry in the stator. Okay. So, this is because for any particular case you require a particular tool, is not it? Just like for any disease you require a particular medicine, right. So, to solve this problem of again steady state analysis of polyphase induction machines with any asymmetrical type of situations. Okay. And this is supposed to be to some extent more powerful than the symmetrical component approach. The important factor here is the presence of space harmonics. We know in practice there would be harmonics in the air gap, harmonics of the magnetic fields in space. So, an ideal single phase winding is expected to give purely sinusoidal variation of MMF in space in the air gap, but in practice it will be either stepped wave or a rectangular wave or a stepped rectangular wave and so on. So, it will definitely have its fundamental, but in addition there will be harmonics. Okay. Now, we said that if a single winding is excited, it will give rise to not only the fundamental fields rotating both forward and backward, it will also give rise to harmonic fields which will be rotating at n times the poles, but at a different speed, that is n by 3 times the speed, is not it, or the if the fundamental has synchronous speed ns, it will be ns by the harmonic number. Okay. So, the frequency of induced voltage will always be same as the fundamental frequency, right. We are not talking about space harmonics, time harmonics. Okay. Now, so last class we said you can write down a volt-ampere equations as a matrix in terms of this impedances Z in the matrix. Each of the impedance will be called a rotating field impedances, okay, associated with forward and backward fields in addition to leakage fluxes. How is the voltage induced? By basic Faraday's law, voltage is induced because of the fluxes and their change with time. Now, we know that if it is a rotating field, it will induce a sinusoidal voltage in a winding in the stator. In the air gap, if you have a rotating field, it will induce a voltage sinusoidal in the stator. Okay. Now, this induced voltage is given by 4.44 Fn5 RMS, where F is the frequency which is fixed, N is the number of turns again which is which will have winding factor for the harmonics, okay, and phi is the flux per pole for the corresponding harmonic. Okay. Therefore, you know that voltage, and that voltage in the current which is producing that flux is considered as an impedance, is it right? So, we call this as a impedance of this. So, we have with this concept last class we have said that we can look at the points as a counter rotating field concepts, then we say it will be a general polyphase machine we are looking at. If we take a general polyphase machine, a symmetrical machine will be a particular case. You can have a symmetrical 3 phase or symmetrical 2 phase, and we can have a general case also, okay, any asymmetrical conditions. Okay. Now, we also reviewed in the last lecture that the MMF produced by a single winding will be having a sinusoidal current, it is not a non sinusoidal current, no time harmonics, and which is stationary in space and pulsating at the frequency of the supply. Now, this is resolved into a series fundamental wave as well as a large number of series of harmonics. This is what we said. So, there will be lot of harmonics in this. Okay. Now, if the winding is symmetrical, then odd harmonics will only be present and no even harmonics, that is what we said. If the windings are symmetrically, if they are asymmetrically made, sort of, you know, if the pitch factor is there, if it is not 180 degrees spread, between the positive and negative phase belts, then it will give rise to even harmonics also. So, you can in general you can take both even and odd harmonics. Okay. Therefore, we also know that the MMF that is produced will be resolved into forward and backward with amplitude 2 equal and opposite fields. Again field you do not get confused, no, field can be both a flux or an MMF, right. So, you be clear, it is the flux is what is the resultant of the stator and rotor MMF. MMF is the potential to which the respective member stator or rotor will be subjected to. It is a magnetic potential. MMF is the magnetic potential and the flux is because of the difference between the magnetic potential between stator and rotor. While MMF is analogous to a voltage in a electric circuit, a flux is analogous to a current in an electric circuit. Current comes because of the potential difference. Similarly, flux is because of the magnetic potential difference between the stator and rotor surface, and it is this flux which is producing the voltage. Okay. Now, so we are clear about, hopefully, on this a stationary pulsating sinusoidal wave can be resolved to 2 equal opposite magnitude of half original, and then it will also be true for all harmonics also. Okay. So, each harmonic component, that is forward and backward, of the stator MMF can give rise to induction motor reaction in the rotor, and we have also said rotor is symmetrical, it is polyphase, squirrel cage or wound rotor, reaction may be slightly different, and this is what it will be. So, rotor, each of the stator MMF will cause a rotor current, okay, and that will produce a rotor MMF, and this resultant will give you the flux. Okay. So, at standstill both the forward and backward will be identical, but at different speeds forward flux is different than backward flux. Is it clear? Okay. Because the rotor reaction is different at different speeds. Okay. So, running condition the fluxes are different, okay, and it has a difference due to the slip. Okay. So, each of the flux wave there are several forward rotating fields, several backward rotating waves, they give rise to the voltage induced in the stator winding. Okay. This is the principle of the rotating field theory. Any doubt at this? So, we are saying that each current passing in one winding will give rise to enough of mesh. Okay. Enough of fields, forward field, backward field induce voltage in its own winding, and it also induces voltages in the other windings in the located in the stator. It may be 3 winding, 4 winding, 5 winding, 10 windings, n windings. So, they will all be having the voltage induced is them. Now, you define an impedance as a voltage induced, you can have a self impedance or a mutual impedance, okay, as the ratio of the voltage induced by the respective currents. Okay. Right. Now, we said that the voltage in one winding, the reference winding will be a drop due to the leakage impedance. Leakage impedance is resistance and leakage reactance. I hope you know about the physical picture of this, but there will be all the forward voltages due to all the forward fields, right. So, if you pass a current I in the one of the windings, it will give all the forward field, it will give rise to a voltage, and all the backward field will also give rise to the voltage, and all will be at the fundamental frequency. So, it is the cumulative effect of all this. Okay. And so, then you can consider this as, because it is sum of the voltages, isn't it? Sum of the voltages. So, that will be, this is represented by ZL, because you take out I, and let us say this ZFN is the forward impedance, okay, and ZBN is the backward impedance. So, what we are now defining is that ZFN will be nothing but VFN divided by the current producing it, is not it? Okay. And ZBN will be VBN, that is nth harmonic, by divided by the current producing that. Okay. So, this is our definition of things. Okay. So, we have seen V is the applied voltage, I is the phase current, ZL is the resistance and coil and reactance, resistance and reactance, ZFN is the forward impedance corresponding to nth harmonic forward field, ZBN is the impedance corresponding to nth harmonic backward field, right. Up to this is, so I have one winding which gets all this produced. Okay. Now, so it will have equivalent circuit contains all harmonic in series with the fundamental impedance. So, it will have harmonics and impedances. Now, we neglect stray losses because the harmonic fields also give rise to stray losses. There are eddy current losses in the core, isn't it? Okay, because they will be creating. So, they go into you look at large machines, some megawatts, even if a minor harmonics is there, it can give rise to considerable amount of losses in the iron, in the tooth, etc. Okay. Now, this stray losses is another ball game, we are not considering. So, we are considering, you know, if you have only one winding, if I apply a voltage V which carries a current I, okay, and so it will have the leakage impedance, then there is a forward first harmonic or fundamental, backward fundamental, and it goes on and goes to nth harmonic, ZFN and ZBN. Is it okay? So, each of them represents a voltage. So, there will be Vf1, Vf2, Vfn, sorry, this is Vb1, Vbn. Okay. I hope you are clear about this. Okay. Now, the point is, if there is one winding A, it is fine. Okay. Now, I keep another winding B, okay, which is at, supposing this is the, so you always take positive theta as counterclockwise though. So, this will be at an angle, let us say theta B with reference to A, okay, and let us say this will have NB by NA is some factor KB. Okay, this number of turns in the B winding is 8, this KB times that of A winding. Is it clear? So, if we have this situation, if a forward field, this is forwards, let us say, suppose it produces a voltage here, let us say VA, okay, then what will be VB? VA, you know, a phasor, what will be VB due to this forward field? It will be, no, first magnitude you tell me, what will be magnitude if it is producing VA in this A winding, what will be in the VB magnitude? Huh? Same flux, no? Flux is same. So, it will be producing KB times VA, but it will not be producing at the same instant as A because it time displaced. It is like train moving from from Delhi to Agra or something. It first touches Delhi then Agra, no? It is forward, but it is backward. So, you can imagine, suppose you take a train from Delhi to Bhopal, okay. Forward train will first touch say Mathura then Agra, okay. So, phase, there is a time phase differentiation, a space phase differentiation of the location of the stations, there is a time phase displacement train touching those stations, obvious, is not it. Now, if a train is coming from Bhopal to Delhi backward, then it will touch the Agra first and then Mathura, is not it? Is it clear? So, this field, forward field will be first, let us say A, then when will it be? It will be e to the power of minus j theta b, is not it? Okay. Now, instead of this forward field, let us say, I mean I will say the V A forward, say, okay, right. Now, if there is another voltage, the backward field is there, this is backward field, which say in this winding which is producing say E A backward, say, I am just giving you some. So, if it was producing E A backward, now what will be E B backward then? If it will be K B into V A backward e to the power of plus j theta b, because this backward field has touched B first and then A. Okay. So, this will happen for several windings, you can have 3 winding, 4 winding, 5 winding, etc. Okay. So, this is the basic logic on which the rotating field theory has been built upon. Okay. So, you have these windings which we said ABC winding, we have just taken 3 first because that we normally do not have many winding, but nowadays people are talking of 6 phase machines, 5 phase machines, okay, polyphase, multi-phase machines, mainly because your power electronics can give currents in the respective phases, right. So, so you maybe this theory may become more handy there, is not it, in such cases. Okay. Now, we have already defined the rotor is of course symmetrical, and now we are taking A phase as a reference, okay, and the number of turns will be KB KC for the fundamental, but it will have another factor KB and KCN because of the winding factors, because pitch and distribution factor for the nth harmonic field will be different. If it is cos beta, then it will be cos n beta for the nth harmonic, because electrical angle will be different for nth harmonic. So, this is due to harmonics, due to the these winding factors. KBN and KCN. Nth harmonic electrical angle is different than the fundamental, because the electrical angle is decided by the poles and your poles are different. Okay. See, you know that pitch factor Kp is, let us say, cos beta by tau, is not it, for fundamental, where beta is this angle between the ingoing conductor and outgoing conductor, right. That is the coil pitch, beta we call it as a coil pitch. These are the your earlier courses you must have done. Okay. Now, the nth harmonic will be cos n beta by tau, is not it. Similarly, distribution factors, right. So, that is why these factors will come to picture. Okay. Now, we are only trying to say that we can make it as an impedance. Okay. So, we have said that VA, VB, VC in the 3 windings will have the impedance IA with the currents IA, IB, IC, we define as ZAA, ZAB, ZAC, ZBA, ZBB, ZBC, ZCA, ZCB, ZCC, is it? Now, what will be ZAA? That will be VA by IA when IB equal to IC equal to 0, simple with this definition. What will be ZAB? What will be ZAB? VB by IA when IB equal to IC equal to 0, isn't it? So, I hope this is a basic circuit concept, you know, right. So, whatever the voltage due to the B winding due to A current, you call it as ZAB, okay. Because the ZAB or ZBA we will say.
So, should not ZAB equal to VA by IB?
VA by IB, ZAB, no?
Yes, sir.
VA by IB when? Okay, yeah, that, but I think this is ZBA is this.
Yes, sir.
ZBA is VB by IA when, that is right, okay. So, you can have all the impedances like this. So, right. Now, you can ZAA will have, we have already seen ZAL and ZFN and ZBN, right. Now, ZAB of course, the we will have KB times because mutual, and that will also have a winding factor KBN, and whatever ZFN e to the power of minus JN theta B, okay, due to forward field. The same voltage means same flux will induce differently, and this ZBN e to the power of JN theta B. So, you have ZAB in same logic which we are trying to say, okay. Is it clear? Because I think this is the point where all of you wanted to be explanation. Is any, okay, then you can write ZDAC with instead of theta B it will become theta C here, okay, and ZBA will be as I told you transpose of isn't it, no conjugate, sorry.
So, ZAB would be the voltage induced in the B winding due to the A phase current. How should we physically?
B winding due to,
Or A winding due to.
yeah, according to that what we have given, it will be B, you know, okay, you can see the definition of that, you know, we in that actually the way we have defined appears to be ZAB, okay, ZAB will be VB by VA by the voltage induced A winding due to B phase current. Oh, yeah, okay. So, I think it is a, but these equations are okay. So, you can, I suggest you can also do your own drawings and make sure that you are, see one is whatever is the voltage induced due to the phasor of the voltage induced in the B winding to A phase current will be a conjugate of the voltage induced in the other windings, okay. So, it is obvious the ZBA will be ZAB conjugate, right. Conjugate will be J becomes minus J becomes J here, okay. I think this is very important. I want you to maybe do your own drawings and make sure that forward and backward field will be induced properly, Okay. Now, the ZBB is what? ZBB is the voltage induced the B winding due to B winding currents. So, that will definitely be its own leakage impedance plus it will be KB square, because KB is the turns ratio of B with reference to A is our reference winding. So, you have this, it will have KBN square. Similarly, ZCC will have, instead of ZCL into KC square into ZFN ZBN. So, the B and C winding will have voltage induced by its own currents, which will be different than the what was happening in the A winding by a turns ratio. Okay. So, but there is no problem of phasor, but phase displacement, if it is the voltage induced in B due to C or C due to B will be the angle between them. Angle between them is now ZB theta B minus theta C. Angle between B and C is theta B minus theta C, is not it? Okay. Because we have already, if we have these 3 windings, okay, we have considered this as theta B and we have considered this as theta C, right, and therefore, what will be this angle will be theta B minus theta C, that is B to C. Okay. So, if voltage induced in one with reference to other will be phase displaced by this angle, okay, due to forward and backward. Forward will be in one angle, backward will be opposite angle. Okay. So, therefore, ZBC and ZCB will have the angles theta B minus theta C, and it will also have the winding factors or the turns ratios will be multiplied by this, okay. That will be KB KC, right, because we are all referring with reference to A winding turns. Okay. This is central to our theory. Okay. Therefore, voltage equations and inspection equations constitute a set of unique equations which can always be solved. We have 3 voltages and 3 currents. So, you have to find out for a given voltage what will be the current, so long as you know the impedances. Okay. So, complete performance of the machine can be computed from these equations. Okay. Now, this method can be applied to the analysis of any induction motor irrespective of winding connection. This is very general equation, right, whether it is wound at 120 degrees, 110 degrees, 90 degrees, you can have this. So, the symmetrical machines therefore become a particular case of this asymmetrical model. Okay. Now, let us take a symmetrical machine. Let us hope that we will have the same equations which we knew earlier. All of you know about the theory of symmetrical machines, okay. But can we get that? Let us see whether we get it or not. If we do not get it, we are in problem. Okay. If we get it, we have no problem. Now, if it is a symmetrical machine, what are the angles? What is theta B is 4 pi by 3, right, 240 degrees, and theta C is 2 pi by 3, okay, because this is purely balanced symmetrical machine. ABC, this is 120 degrees and this is 240 degrees, and KB KC equal to 1. Therefore, nth harmonic also it will be same 1, and ZJL equal to ZBL equal to ZCL, leakage impedance will also be same, they will have same resistances, same leakage reactances, symmetrical winding. So, you are safe, okay, ZL. So, you can write, so ZAA equal to ZBB equal to ZCC, which will be A, we can say, both are same, that will have its own ZL, and the sum of all the ZFNs and sum of all the ZBs, okay, that we have. So, that will be the self impedance of the 3 windings ABC. Okay. Now, what will happen to ZAB will become ZBC equal to ZCA, because they are all at 120 degrees, okay, and you call it as B, that will be a to the power of n, a is e to the power 2 pi by 3, z f n and a to the power of 2 n z b n, because you can just substitute those values, and z s is equal to z b a equal to z c b by symmetry. Okay. That will be a factor c, constant c, which will be a to the power of 2 n into z f n plus a to the power of n into z b n. I want you to just check this. If you have doubt, you have to get it clarified. Okay. How you get this? Because you had to substitute for that general equation, substitute the constraints. Okay. And therefore, we have this equation V A V B V C will be this matrix. So, you can write in a matrix form V A V B V C will be A B C C A B B C A of I A I B I C. Okay. Now, we have already defined what is ABC constants. Now, let us try to find out what is ABC constant different harmonics, because let us not go into too many, maybe let us say first, second, third, etc. Okay. Now, if it is symmetrical voltages, say now this was symmetrical machine, voltages will be V A is equal to V, V B equal to A square V and V C is equal to A V, is not it. So, you have 3 phase voltages you apply, if you, this is V A, this is V B and this is V C. So, if you say V A is a voltage V phasor, okay, that is what you will have. Okay. So, you can always expect that due to the, this is due to the positive sequence I A 1. So, it will produce I A 1, I B 1, I C 1 are the currents due to positive sequence voltages. Okay. So, this is positive sequence voltages. Positive sequence operation is this, and you expect, therefore, the currents are these I A 1, I B 1, I C 1 may be I A 1, I B 1, I C 1 for the applied voltages V A 1, V B 1 and V C 1, and you call this angle is, let us say, theta usually, okay, fundamental whatever it is. Okay, then okay, now we can call this, that will be I A will be voltage divided by A plus A square B plus A AC, I B 1 will be A square B or A plus A square B plus AC, and I C 1 is A V or A plus A square B plus AC, right. So, it will be whatever is the V A 1 divided by Z 1. Okay. After all, is not it, I A 1 will be whatever V A 1 by Z 1, I B 1 is V B 1 by Z 1 and I C 1 is V C 1 by Z 1. Okay. Is not it? What is Z 1? We can call it as the positive sequence impedance which includes harmonics, right. So, we can define Z 1 is the positive sequence impedance which includes harmonics and defined as V A 1 by I A 1 which is also equal to V B 1 by I B 1 equal to V C 1 by I C 1. Is it okay? And what is that value we got? A plus A square B plus AC. Okay. So, this is equal to and we have defined ABC, these constants, agreed. So, it is a question of substitution. Okay. Let us do that. Now, by substituting we will expect, we can verify this, ZL plus 3 times ZF1 plus ZB2 ZF4 plus ZB5 plus ZF7. Okay. This is what you will get, and if you neglect the even harmonics, if it is symmetrically arranged, if only odd harmonics are there, the positive sequence impedance will consist of the leakage impedance plus 3 times ZF1, that is due to forward field only, fundamental, and ZB5, that is the 5th harmonic backward field, and ZF7 the 7th harmonic forward field. Have you ever come across this earlier in your, have you? This, does it ring any bell in your ears? We have said that forward there is, if you apply a 3-phase balanced voltages to a even a symmetrical machine which has harmonics, what are we saying? There will be, it will still have a 5th harmonic backward field, okay, but it will also have a 7th harmonic forward field. So, there will be a forward field which is 7th harmonic, means it will be running at 1/7 the synchronous speed. What is this phenomenon called? Crawling. So, what will happen is, if it is a badly designed machine, it will crawl at that speed. So, instead of running at 1500 rpm, it will stop at 1/7. Okay. That is an interesting observation which I got from this theory. Okay. So, what it means is, if it is a squirrel cage machine, you would have expected the normal fundamental field will give rise to this, is not it? Okay, torque due to fundamental, this is 1. Then what we are saying is, there is a 7th harmonic forward field, forward direction, it will, if this is ns, it will be 1/7. Okay. So, it will give rise to torque speed characteristic. How will that be? It will give rise to some torque speed characteristic like this, right, and there is another, say at 1/5 minus n, because this is other direction, ns by 5 minus backward. So, it will also give rise to its own, this is a 5th harmonic backward torque speed characteristics. So, the net will be somewhere, there will be a possibility of some dip here, right. So, superpose on this some characteristics, okay, this character superpose here. Right. So, you might end up with a another characteristics which may be something okay, let us say it will go something like this. This is the net, is not it, right. Now, what will happen is, supposing you have a load, maybe this is the load, okay. If it is load, it will see at some speed here a very stable point. This is stable, is not it? So, it will start running at 1/7 the speed, okay, and this is called the crawling. At 1/7 speed. It will not go to the full speed at all, otherwise it should have been running here, because after all it is load characteristics cutting the motor characteristics, that is where it will run, is not it. At what speed a fan will run? That means at a speed in which the developed torque is equal to the opposing load torque of the blades. That is what speed a pump will run. The pump will run at a speed in which the developed motor torque is equal to the opposing torque of the water and the friction of the pumps and the blades, is not it. That is what, so this is the load characteristic. If this is a load characteristic, it will not, but of course if it is a load like this, there is no problem, where it will not cut this curve. Okay. Now therefore, I think you need to see this A plus A square B plus AC you have to find out. Okay. What is that value? I think ZL A plus A square B plus you substitute here, that is what we are saying is Z1. Okay. So let us say this A plus A square B plus AC, right. So we have said what is A is ZL plus ZF1 plus ZF2 plus ZB1 plus ZB2 plus ZF3 plus ZB3, this is what it is, and B will be AZF1, okay, AN, no, right, AZF1 plus A square ZF2 AN ZFN, right, and C is, what is C? Is A to the power of 2n ZFN, means A square ZF1 A square ZF1 plus A to the power of 4 ZF2 A to the power of 2n ZFN, is not it. So you are trying to say what is, I am just wanted to have a few numbers, A plus A square B plus AC, is not it. Yeah.
It will also contain ZB terms.
Yeah, ZB also will be there. No, I am just trying to I mean plus the ZB, yeah, ZFN of course it will have, ZP terms also will be there. Yeah, I am just trying to, these will also be there. So you have to go on summing it up. I thought the board is small enough, you can't write everything. Now if you do that, A plus A square B plus AC, so you can say ZL of course will be there. Now you take the ZF1 term, so it will be ZF1, A square B is again ZF1 and AC is again ZF1 plus 3 times ZF1, is not it. I am just trying to say. Now what will be ZF2? Will it be there or will it not be there? No. Now I think for a simple thing you can neglect the even harmonic, go to the odd harmonic. Okay, let me see ZF3. ZF3 will become, that will not be there, no. ZF3, if you say ZF3, it will be ZF3. This will also be ZF3 in, okay. Now the sum of this Z1 plus A square plus A is 0, so there will be no ZF3. So it will be 0 into ZF3. Okay. Now you go to ZF, that is why I am saying even so you will not have 3 forward, you will not have 5 forward, you will only go to 7 forward. So that is why you are saying 3 times ZF7. Okay. I think you can, this is purely a algebra for you. So you just check this, right. So, I assume that whatever I am writing you are prepared to accept, okay, right. So, we say that Z1 is given by this ZF 3 times ZF1 ZB5 ZF7, okay. Now, if you similarly you can do negative sequence operation. So, negative sequence will be you have made the applied voltage opposite to this, okay. So, obviously VA is V, VB is AV and VC is A square V, is not it? It is simple. Now, you can follow the same logic to say that I will have it will also produce IA2, IB2, IC2, okay, and which will be VA2 by Z2, VB2 by Z2 and VC2 by Z2. Now, here it will be that it will be V by A, AB, A square C, right, and this will be A, AB, A square C. So, your Z2 will be A plus AB plus A square C, okay. So, it is again a simplification. You substitute for ABC which we have already derived earlier and make the simplification, right. So, your currents will be negative sequence currents, these are negative sequence currents. So, for a 3 phase symmetrical machine if you apply negative sequence voltages, that means opposite phases, so it will give rise to negative sequence currents. Of course, if you have unbalanced it will have both positive and negative sequence voltages, okay. Therefore, the Z2 simplifies as follows, Z2 will be ZL into 3 times ZB1 now, because ZF1 will vanish, it will be 3 times ZB1, of course then ZF2, ZB4, ZF5, ZB7 etc. And if you remove the even harmonics, so you will have this only odd harmonics. So, what will you get here? So, the this will be Z2, therefore, negative sequence impedance will be ZL plus 3 times ZB1, it is not ZF1 and now ZF5, okay. So, it is almost like a mirror reflection of the positive sequence systems and then ZB7, right. So, the backward 7th is predominant and forward 5th is predominant, okay, and these are the fields which will be predominant which will impact on the performance of the machine, okay. Now, just one second. So, we can also complete with 0 sequence also, right. 0 sequence what you have said is all are same VA, VB, VC. So, therefore, VA equal to VB equal to VC equal to V and the same thing will give rise to the 0 sequence currents. So, it will be let us say VA, it will create Z naught. Z naught is a 0 sequence impedance which will be nothing but 0 sequence voltage by 0 sequence current. Z naught is VA naught by IA naught which will be same as VB naught by IB naught etc. Okay, simple. And though, but this here the factors are coefficient is A plus B plus C. If you just take A plus B plus C, okay, then you will have what is this? This is Z naught, right. So, interestingly, if you do this, A plus B plus C will be ZL plus 3 times ZF3, ZB3, ZF6, ZB6 etc. If you again if you remove the even harmonics, interest Z naught will be equal to ZL plus 3 times ZF3, ZB3, ZF9, what does it say? Only triplen harmonics, both forward backward. So, what we the conclusion we get is 0 sequence is due to triplen space harmonics. A 0 sequence operation, if third harmonic is there, your machine can run at 1/3 the synchronous speed, if there is a predominant third harmonic. Okay. So, that is an important conclusion that we can draw, that 0 sequence, but what we did in the earlier case, we neglected 0 sequence and then we got what impedance. If we neglect 0 sequence, what you have is ZL only. So, we had earlier had said that your Z1 will be ZL plus 3 times ZF1 and Z2 is equal to ZL plus 3 times ZB1, and we said that Z0 will be ZL only. This is what we had done earlier, because we did not take the space harmonics into account. Now, you will see taking space harmonics into account, it will make you much more enlightened on what happens physically inside. Okay. So, we will stop it here and we will take it with 2 phase machines next. Okay.